area between curves. So far in this course of calculus, we have only considered the application of integrals to find the area under simple curves, whose graphs are above the x-axis. But, of course, a graph can go below the x-axis. We now consider this situation, and then we consider the area between curves. Thanks in advance for watching this video. If you like this video, don't forget to like and subscribe to the channel and activate the bell. It's very important for the continuity of this channel. When a graph goes below the x-axis, the corresponding y value is negative, and so the value of the definite integral is negative. Therefore, when an integral turns out to be negative, you know that the area is below the x-axis. The area is negative, and we take its absolute value. Find the area of the shaded region below. We can see that the area is below the x-axis, so the area is negative, and we take its absolute value. We now perform the calculations. From our discussion above, when the graph goes below the x-axis, the area is negative, and we take its absolute value. But sometimes the graph is partially below and above the horizontal axis. The area between x equals a and x equals b is negative. When the curve crosses the x-axis at x equals b, the values of the function go from negative to positive, and the area between x equals b and x equals c has a positive value. Therefore, we consider the absolute value to ensure all of the enclosed area is counted as positive, and we use the following formula that joins these two results. Suppose that we have a function y defined and integrable on an interval from a to c. Then the area between the graph of y and the x-axis for x in this interval is. We split the integral up into two parts, and the area becomes. Let us solve one example to make the theory clearer. Find the area of the shaded region below. To find the shaded area, we split the definite integral into two parts. Then evaluate each integral separately and sum them up. Pay attention. In the previous examples, we saw how to find the area between the graph and the x-axis in regions where the function is positive or negative. We can now extend the application of definite integrals from the area of a region under a curve to the area of more complex regions, such as a region between two curves. Suppose that we have functions f of x and g of x defined on an interval from a to b. Then, the area between the graphs for x in the interval from a to b is the difference between the definite integrals of these functions. and we write these differences as follows. Let's solve the following example to make the theory clearer. Find the area of the shaded region below. From the graph, we can see that f is greater than g in this interval. So the area between these curves can be calculated by making f minus g. We now perform the calculation. This example we just solved is very simple. Now let's solve more challenging examples. Find the area of the bounded region between the graphs. The region whose area is in question is limited by the curve f and g. Firstly, we need to find the points of intersection of the curves by solving their equations simultaneously. The points of the intersection of these two curves are given by the parabola and straight line intersect when x equals 0 and x equals 3, and 0 and 3 are the limits of integration. To be clear about which of the two functions is larger, you should always sketch a graph of the region. Without an outline, it is often easy to confuse which of the two functions is the greater. We now apply the formula above to find the area of the region between the two curves. Let's solve another example. Firstly, we need to find the points of intersection of the curves by solving their equations simultaneously. The points of the intersection of these two curves are given by the parabola and straight line intersect when x equals 1 and x equals 5, and we can observe that the points where the graphs intersect are not the limits of integration. So we should always sketch a graph of the region. We can observe that between x equals minus 2 and x equals 1, f is greater than g, and between x equals 1 and x equals 5, g is greater than f. So we write the area as a sum of integrals over the two intervals. We now perform the calculations. So far, we have calculated areas between curves and the x-axis, but we can ask it to calculate the area between a curve and the y-axis. In such cases, the integral involves the y and not the x. It is therefore necessary to write x in terms of y wherever it appears. The integration is then said to be carried out with respect to y instead of x. Let us solve two examples to make the theory clear. In this example, we are being asked to calculate the area between a curve and the y-axis. So we use the equation of the curve as x as a function of y, because the integration will be carried out with respect to y instead of x. We now perform the calculations. Find the area enclosed by the line in the parabola. The area is the region bounded on the right by the graph of the straight line and on the left by the graph of the parabola. We must first express the graphs as functions of y. Now we have to determine the limits of integration. The points where the two graphs intersect determine the lower and upper limits of integration. Now we must determine which function is the largest and which is the smallest for y between -2 to 4. We can do this by rotating the graph by 90 degrees. We can see that the equation of the line is greater than the equation of the parabola in this interval. We can write the area as follows. We now perform the calculations.